Okay, as promised, I'm going to do number 2 for us off that worksheet on solution stoichiometry. Before I actually begin, though, I'd like to just talk a little bit about what we actually know that we can do at any time. Okay, we have molarity, which can be somewhat intimidating, but know that anytime you have molarity and volume, okay, you can easily get to moles. Okay, moles are usually fairly simplistic to deal with. What I'm talking about is doing stoichiometry and that type of thing. You know, if you're at moles, you just do the mole-to-mole ratio. Life is usually easy when you're at moles. Molarity, on the other hand, molarity can be somewhat intimidating for us to deal with, somewhat scary. But all I'm saying is before we actually start working the numbers here, know that anytime you have molarity, you can always get the moles, okay, via the volume. Okay, also note that volumes are additive. Okay, what I mean by that is if I have, a beaker of 50 mils of solution, another beaker of 100 mils of solution. When I add that up, okay, this is 100 mLs, this is 50 mLs, you eventually get 150. Okay, this looks like common sense, but to be completely honest with you, it usually doesn't work this way. Okay, we're assuming volumes are additive, but there actually is a little bit of a discrepancy on the reactions themselves. What I mean by that is sometimes when you're making a precipitate, okay, you remember the precipitate was in solution before and now it's not. The actual liquid volume of what is left is not entirely always additive. So this seems like it should be common sense, but in actuality, we're actually assuming something that in a lot of ways, in many examples, it's actually false. But it's actually close enough. If you weren't going to do these assumptions like assume volumes add up, then you'd actually only be able to do these types of things in the lab because there's no way to really predict. We don't have an equation to predict the way the volumes will actually decrease. Okay, so know that molarity, if you have volume, can always get to moles. Know that volumes are additive, so your final solution will be both volumes added up. Okay, these are just little tidbits before we actually start working on any type of problem. Okay, also know, anytime you have, a compound, you can do some math to get to number of ions or number of atoms. Okay, what I'm saying is if you know moles of the compound, you can always get number of ions or number of atoms of that compound. What I mean by that is something like this. If you have 5 moles of H2O and you wanted to know how many H's you had, H atoms, it's not an ion because it's not an ionic compound, for every 1 mole of H2O, there are 2 moles of H atom. Okay, so know that anytime you have a compound, you can also always start talking about the parts of the compound, such as the atoms for covalent compounds or the ions for ionic compounds. Okay, so just a couple things in our tool bag that maybe we should have if we would have went over this couple little tidbits, maybe things would have been slightly less confusing. Okay, but like I said, I feel rather uncomfortable telling you exactly how, a way to actually solve more of a complex problem. I really like people sweating it out and thinking about it. And take our class, for example. We've done a lot of AP chemistry quality work, specifically in the whole intermolecular forces, the Lewis structures, molecular geometry. That's all totally AP quality work. And it's work that you can be proud of to know. But I don't feel to this point that we've done a lot of problems that when you solve it, you actually feel a sense of accomplishment. Okay, and that's actually very important for me, to have that sense of pride, to invest 20, 30, 40 minutes in a single problem and come up with the right answer. Yeah, I actually get, somewhat euphoric even to this day. I'll have, a couple weeks ago, I had an AP student come in for help, and we were doing our online chemistry homework somewhat together, and each time we were clicking submit and almost crossing your fingers and waiting for that green check mark and seeing the green check mark and being so excited that you got the answer correct. Now the flip side to that would be getting the big red X for the wrong answer, and that you have to put yourself into a position of not being deflated, but almost re-energized in order to conquer the problem and to figure things out. Okay, don't get deflated and you sulk and feel that you can't figure it out, or I just don't get it. But no, take it as a personal challenge and invest another 20, 30, 40 minutes into analyzing work and maybe possibly finding an error. Okay, and I feel that some of us actually need to experience that. That's actually a key goal of mine with the class, is to get us a sense of independence and a sense of can do, that you can actually pull things like that off. Okay, looking at our problem. 7 minutes in. Okay, there we go. Okay, looking at our problem here, we have barium nitrate, certain volume and molarity of barium nitrate, combining with our sodium phosphate. All right, so just to write our reaction out here, and let's do it up top. We have our barium nitrate, which is going to be BaNO3, 2. And it's a solution, so it's aqueous. And we're adding to that sodium phosphate, which is going to be Na3PO4. And since it's a solution, it's aqueous. They're going to react and form a precipitate. Okay. Some of us might have to review the rules for that, but I know that all of my alkali metals are, and all of the nitrates for that matter, are soluble. So I know that my reaction is going to be an aqueous for the sodium nitrate, and I know that the barium phosphate is going to be our solid. Okay, so that's our actual full molecular equation. Okay, I said molecular because I'm keeping them in the molecule form. I'm not doing net ionic. We might do a little net ionic work later, but as of right now, I'm going to leave that up there as the full molecular equation. And that's because our first question, calculate the mass of the precipitate, is very, very familiar and very, it's basically the same as the stoichiometry we've been doing. Okay, the only twist is that you start off not with a mass, not with a liters, not with a number of atoms or molecules. We're starting off with a volume. Okay, we're starting off with a volume, and we have our molarity as a conversion factor. All right, because we want to start with something that actually has numbers to it. Volumes of gas is one thing that actually has meaning. Volumes of solution, since it's two things mixed, doesn't give us any information. The molarity is what gives us the information, the concentration. Okay, so we're going to do our two stoichs based off of our both starting points of our volume. Okay, and I'm going to do these concurrently, both stoichiometries at the same time, because it's a limiting reactant problem. Okay, it doesn't say anything here about being a limiting reactant, but that's something that I'd expect you to be able to see because you have information on both. Okay, you have information on both reactants, so it's obviously limiting reactant. And I'm going to start both of them off and do both at the same time. Okay, so I'm going to do my metric conversion and say 0.045 liters of barium nitrate. And I'm going to convert that over to moles via my molarity. All right, so we're in moles now. We got rid of our volume via the molarity, and liters are gone. Okay, I won't cross them out just so we can not get too sloppy here. I can already see we're going to have issues here with the rest of the problem squeezing it in, so I'm going to have to write smaller. Okay, we're in moles. We need to get to our barium phosphate, so we're in moles. It's time for the mole-to-mole ratio. Something I didn't do yet, I'm going to switch colors for just so we can see, is the balancing. Okay, it looks like I'm going to meet at 6. Okay, I'm glancing at this reaction very quickly, and I can already see that we're going to have to meet at 6. All right, and this is a 2. I'm sorry, so we're meeting at 6 for our sodiums. So I'm going to go ahead and do that. All right, with a 3261. Okay. So using our balanced equation to finish this out, we're going to see that it is a 3-to-1. Okay, 1 mole of Ba3PO4. And they're looking for, a mass, so we have to get to grams. And I'll look up the actual mass here in a second and put that on top here. It's going to be Ba3PO4. Looks like that. Like I said, I'll do the other one concurrently, so I'm going to do this one a little different. I'm going to start with the 35 mLs. Okay, of Na3PO4, and a little bit of a twist here. I'm going to say 0.54 molar of Na3PO4, and I'm going to say 1,000 milliliters on the bottom. All right. Not a big change, but what I'm saying here is I did the mental conversion here. Instead of 45 mLs, I start with 0.045 liters. In this one, I kept it as the mLs and did the conversion here. Okay, there's a third option. A third option is to start with the milliliters and then do a 1 liter on top, 1,000 mLs as your second step. I prefer these two ways just to make life a little shorter time-wise. I think we all have, the basic centimilli-kilo metric system down. If you don't feel comfortable doing that, of course, you can just slow it down a little bit and do every single step with the metric conversion. This is a 2-to-1. Trying to write a little smaller here. Again, I'm going to have to look up our molar mass for this one. And I shall do that now. Okay, we had, I looked it up, 602.1 grams of barium phosphate in a mole. So I put that in there and did their calculations. From what we see here, we have the answer to A. Okay, is 4.88, meaning the barium nitrate is the limiting reactant, and we have excess reactant of sodium phosphate. Okay, now in part B, they're asking percent yield. Hopefully you see that it is actual real life value over the theoretical value, which is our calculated amount, times 100%. Looks like we're about 2/3. All right, what's my answer here? I'm going off memory. I think it was 68.1. Okay, yes. Okay, so that handles A and B. And we have to appreciate that, you know, those were somewhat similar to our regular stoichiometry. Okay, question C can be a little intimidating. First of all, I'll tell you that it's a little bit more on the difficult side. We've already know that. Also, it's kind of nice to see that it's a difficult question and it's not, you know, what is that, 8 or 9 words. Okay, it's always interesting that it doesn't have to be the paragraph story problem that we see in physics and math and chemistry to be somewhat labor intensive. Okay, you can have a simple command like determine the concentration of each ion still in solution. I don't like the word floating. Okay, so they have a simple command of a few words, but it's going to take us a little bit of work to actually figure that out. Okay, so let's think about this. Let me erase a good chunk of this here. I'll tell you what, I'm going to leave a lot of this on here. Okay. I'm going to put up, we had 0.045 and put that back up there. All right. Ignoring everything on the screen except perhaps the reaction here. They want to know the concentration of each ion left. Okay, meaning the ones that are still in the actual beaker. And for those of us at home that need a little bit of a visual cue, here's my beaker. Okay, I poured in my sodium phosphate, and I also poured in my barium nitrate. And I have my beaker here, and I have the precipitate at the bottom. Okay, this was going to be my, I guess I'll just label this one the barium nitrate. And this is my sodium phosphate. And the crust that I get on the bottom here is Ba3PO4. All right, and we said our limiting reactant was the barium nitrate. And our excess reactant was the Na3PO4. So that's exactly what happened here. We dumped our 2 beakers into a bigger beaker. Okay, they didn't say that, but I mean this setup perfectly works. We dump our 2 beakers into a bigger beaker, and we get a solid on the bottom. I'm going to take a second here. I want to write the actual net ionic reaction. Okay, barium nitrate, sodium phosphate, and I make my precipitate. All right. I'm going to do the net ionic reaction. If you split everything up and you cancel out spectator ions, you're actually left with this. You have 2 phosphates and you have 3 bariums. Okay, note the way I do net ionics is these are aqueous. I just build the precipitate. Okay, it's a little trick that will make life much easier for you if you take AP chemistry. So I know it's precipitation. I started with my actual, I'm sorry, that's a solid. I started backwards from the product and worked my way back to the reactant side by building up the solid that I created. Okay, obviously you can do it with breaking everything up and canceling out spectators, but if you're comfortable enough doing it that way, go ahead and do it that way. So this is the actual chemistry that's occurring. Only our bariums and our phosphates really matter, and they form the precipitate. The other ions are spectators. And more specifically, I want you to look at our work here below that we already identified the limiting excess reactant. We know that the phosphate is coming from sodium phosphate, and it was the excess. Okay, what that means is you're going to have leftover phosphate, and we know that the barium's coming from barium nitrate, and it's limited. Meaning you run out. You will not have any leftover barium. The barium ion is gone. It's 100% converted over to barium phosphate. The phosphate came from our excess reactant, so we have extra phosphates. Okay. What else do we have extra of? We have our extra nitrates and extra nitrate ions and sodium ions. Okay. Because they weren't used. So those are the three things that we're looking for: the excess phosphate, the excess nitrate, and sodiums. And they want those in molarity format. Just erased my answer. I'll have to refer back to, but that's okay. All right, so this was our Stoich to begin with. And I'm going to change this. I'm going to look for, we already identified that the nitrate, okay, the nitrate ion is excess. So I'm going to change this up, and I'm going to look for nitrates. There was a little 2 there, I erased. Okay, for every 1 mole of BaNO3, there are 2 moles of nitrate ion. Okay, so that gives me the actual data to know how many moles of nitrate I have. And just doing that really quick here, instead of hitting pause, I'll make you suffer through. I see that it is 0.0486. Okay, so it's 0. That's my eraser. That's my eraser. All right, that's my erasers. Oh, I had the stylus upside down. I will say that that's never happened before, but you can choose not to believe me if you wish. Okay, so we have our moles of nitrate. That's one of the ions in the solution still floating, their words, not mine, in solution. Okay, so they're asking for the molarity. Get us a little bit more room. They're asking for the molarity of the ions. So the molarity, and I'm going to do something we haven't seen. I'm going to put brackets around, okay, around nitrate. The brackets actually mean molarity. So anytime here on out you see brackets, it actually means molarity. It's going to be 0.0486 moles, okay, over not 45 milliliters, okay, or 0.045 liters. We can't do that anymore because volumes were additive, okay, over 0.080 liters. And that's going to give me my molarity of my nitrate ion. Looks like it's 0.608. Okay, so it's upside down again, so that's the second time that's ever occurred. 0.608. Okay, I'm going to say moles per liter. So that's the molarity of our nitrate left. The molarity of the sodium is going to be the same format for every 1 mole of Na3PO4. I have not 1, 2, but 3 mole of sodium ion. All right, so 0.035 times 3 times 0.54, skipped a step, is 0.0567. So 0.0567 mole of Na plus 1. So this is the moles of sodium. Again, we can use our starting values because there is no product. There are many ways to do this. We could actually go all the way to sodium nitrate and then figure it out from that. And that's actually not even a long cut or a longer version. But I prefer this method because since they're not reacted, our nitrates and our sodiums, we might as well just start with what we're given in the problem. So that's what we did. We found our nitrates moles that we started with, and we can use our starting value because they didn't react. And then I also found our sodium moles that we started with, and we can use our started with value because they didn't react. So my molarity of sodium is 0.0567 over, again, 0.080. Putting that through our calculator, and we get a 0.709. Okay, I'm just going to call it moles per liter here. All right, so we have 2 of the 3 excess molarities. So we have 2/3 of C done. And those are considered, I would say, the easy ones. All right, so we have our nitrates and our sodium ions complete. But now we want to know about our other excess, and that would be our phosphates. Okay, our phosphates, we said that because it came from the excess reactant, we, something with my calculator here, we have excess phosphate. Because we had excess sodium phosphate, we're going to have excess phosphate ion. All right, so to do this, for the excess phosphate, we're going to have to do a little math on this. We're going to have to know how much we started with. That's the easy part. Okay, I could have amended what I just erased in order to put that up there. We have to know what we started with, and then we're going to have to start with or subtract what we used. So this is our started with, and minus what we used. Okay, or you used in a net ionic fashion actually means, the product of phosphate. Okay, what was produced from the phosphate would be what we used. Okay. If you remember, we had 4.88 grams of barium phosphate produced. Okay, so to find out how many, we can use any unit for this, okay, grams or molarity or moles. We want molarity, but I think it's easier to stay in moles. So just to be clear what we're doing here, I want to find moles. Because again, molarity is easy. It's confusing, but it's easy if you split it up into moles and then make molarities afterwards. So that's what we're going to do. If you remember, we created our actual product of 4.88. We're just going to go backwards again. 602.1 grams BaPO4 2 in 1 mole of Ba3PO4 2. And again, this is going to be the phosphate used. We're going from our product, and I'm going to say for every 1 mole of Ba3PO4 2, there were 2 moles of PO4 minus 3. And when we do that, we're going to get moles of phosphate used. All right, so I'm going to say answer mole PO4 minus 3 used. For the other side of the coin here, for our starting material, again, I erased my math from the first section when we found the excess sodium. I could have easily used this information, but it won't take me but a few seconds to put it back up there. 0.035 liters of Na3PO4. Okay, and in this I had 1 liter of sodium phosphate. We had 0.54 moles. And in this, for every 1 mole of sodium phosphate, there's 1 mole of phosphate ion. And just to be clear, this is going to be the moles of phosphate from the get, okay, from the initial starting point. Might help if we introduce another color here, the sea of red. It's awfully intimidating. It's as if we're doing something radically wrong. Okay. Instead of pausing, I'll let you hear me calculate this. 4.88 divided by 602.1 times 2. All right, when I did that, I come up with the answer of 0.0162. 3 sig figs. On the flip side, 0.035 times 0.54. I get an answer of 0.0189. Okay, first, do those numbers make sense? What I mean by that is, look at, we started with a bigger number and we used a smaller number. Okay, that makes sense. We used a great portion of our phosphate, but it was still in excess nonetheless. So, leaving that information up, okay, and just amending this equation that we did, it's going to be 0.0189 mole minus 0.0162 mole of the phosphate ion. And when we do the math on that, we're going to equal 0.0162. I'm going to equal 0.0027 mole of PO4 minus 3. Dot, 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 dot to bring down the excess. Okay. So that's how much we have left. Okay, that's how much is in excess. But again, they're looking for the molarity in excess. Okay, our quantity is in moles. It's the right answer, but not to their liking because they're looking for the molarity of excess. And when we find the molarity, we're going to have to put it over 0.080. Again, that was our volume. And when we do so, we're going to get an answer of 0.0338 mole phosphate over liter. Okay, so we had a problem that seemed overly complicated. I know I really spent my time going over it. Okay, but hopefully you see that there really isn't anything new here. Okay, we're just using the tools that we accumulated. Okay, this problem here, from writing the initial reaction, balancing it, using our solubility rules, using all forms of conversions, using stoichiometry, using net ionic reactions. Okay, this problem is almost like a test in itself. It has basically every single concept that we've covered since the midterm all rolled into, I don't know, roughly 35, 40 words. Okay, so it's fairly incredible that we're actually seeing that these things are starting to build on each other. And at any one time, you're expected to be able to pull off individual concepts, piece them together, and make some magic with it. Compared to studying a specific type of problem and knowing how to do that specific type of problem, now I can actually ask you things that are combinations of different problems, and hopefully you can see that there's an evolution there. So hopefully you find the 36 or 37 minutes an advantageous endeavor of your time. So there goes question number 2.